question from Prarana, and let me first pick up that question. And in the meantime, if you have any questions, just let me know. So the question from Prarana is, if we use the PCA, okay, scaled, what are these two lines of codes are doing? First line is fitting the model, and the second one is fit transform is doing dimension reduction. Also, what does the output table reduce here contains? I know they are not given eigenvectors. So I think this is yesterday I was referring that the PC final, this is nothing but we are estimating the betas. You remember each fact analysis, each component is a linear combination of variables. And when you are transforming this one, so basically x1, x2, x3, suppose x4 you have it, and you are creating a PC1, PC2, PC3, PC4. So suppose this one, it will give me just the betas, the equations, and this one will give me the PC1, PC2, PC3, PC4, which is nothing but a beta 1 1 times of x1 plus beta 1 2 times of x2 plus beta 1 3 times of x3 plus beta 1 4 times of x4. So this is the PC1. So that values will be calculated based on these values, and whatever you got it from the, whatever you are getting from the model, I mean the model is nothing but the fact analysis, the betas you will get from here, and the x1, x2, x3, x4 you are getting here, and just you are calculating the components. So the reduced CR is nothing but these values you will have it. Okay, are you clear? Prerna, is that clear?
Yes, Chandra. So yeah, so just the first one is just fitting the model, right? And the second line of code is creating those PC values across all rows and all
Correct.
components.
Exactly.
Okay, thank you, Chandra.
No problem. Any other questions? I could not follow your question. How can we apply
classification to variables with more than 2 categories?
Classification method for more than 2 categories. So basically you are saying that a multinomial classification. Okay, so the multinomial classification, if you have a logistic regression, I told you there are two types of logistic regression. One is a binomial logistic regression, and one is a multinomial logistic regression. So this is one method you can use it. And in the classification techniques, we also look at some more classification techniques like decision trees or random forest, bagging or boosting or KNN, SVM. All of them works both binomial binary categorical variable and multinomial categorical variable. So there is no difference. Only in the logit is logistic regression, it will only applicable to binomial. But if it is a multinomial, what we will do is, suppose you have customer ID x1 and x2, x3. Suppose you have y. Y is assuming that you have high risk or medium risk and a low risk. Suppose this is the category you have it. So we will create 3 high risk and just like medium risk and y low risk. So just like a dummy variables, what we do, wherever high risk is there and remaining are zeros. So then you will build one model by taking this as a dependent variable, and you will build another model for by taking this as a dependent variable, by building another model depending on this variable, and the probabilities you will get it. Those probabilities will be a probability of y equal to high risk and probability of y equal to medium risk, probability of y equal to low risk. So that is comparison you can do. So this is a typical multinomial logistic regression. When you do that, this is one versus others. That is will take, and that's how the multinomial model will be built if it is a logistic regression case. Okay, but other models like KNN, SVM, decision trees, etc., you don't need to come up with this kind of thing. There they have direct option of doing the models. The confusion matrix, there you will not have a sensitivity, specificity, etc. There you have a classification report. How many ones, how many high risk customers you predicted as high risk, how many low risk customers you predicted as low risk. So just you will get a confusion matrix, 3x3 matrix or 4x4 matrix, depends on the number of categories. But you will not have a sensitivity, specificity, TPR, TNR, those things you will not have it here. Because in the multinomial classification, there you can't have a 1-0 kind of a thing, right? Any other questions? Guys, any other questions? Okay, so if you don't have any further questions, let's move to the next topic. I think we finished regression problem and the classification problem and the segmentation problem. And let's start with the forecasting problems. So what is a forecasting problem, guys? What is the forecasting?
Predicting a value based on past.
Predicting a value based on the past. What does that mean?
So it's under predicting a value, taking time in consideration, past time in consideration.
Okay, so basically you are saying that predicting a value over the time. So the regression perspective, we don't really talk about what is a time frame. But in this case, okay, what is the sales in the next 3 months? Or what is the customer spend in the next 6 months? Right? So that is the, when we are referring to the data or predicting a value indexed by time or over the time, and that is what we call it as a forecasting. Right? So can we tell me what is the typical applications of forecasting? What are the typical applications of forecasting? What even weather forecasting means?
Predicting weather conditions.
Predicting?
Weather conditions.
Okay.
Weather forecasting, sales forecasting, procurement forecasting,
Okay.
inventory forecasting.
Okay. Okay. So I think weather forecasting or stocks forecasting or maybe all macroeconomic factors like what?
Yes, GDP.
GDP, inflation, employment rate, yeah, whatever it is, that's opposite, right? So like this, you can see some of the macroeconomic factors, and the most important thing in the manufacturing industry, etc. So the demand forecasting. So demand, how much demand we have for a particular product. So based on that only they will manufacture it. Typically the inventory management or vendor management, etc. They will take care of, demand forecasting. And the resource forecasting. What do you mean resource forecasting, guys?
Market.
So resource forecasting is like, but it can be HR or it can be ingredients or any kind of a thing. So most of the times the workforce planning. So resource forecasting, I mean to say the workforce planning, how many resources required for a fulfilled particular thing. So these all are a demand forecasting or workforce planning, etc. Accordingly we can plan it. Okay, and in the marketing, this kind of a thing, a lot of times customer lifetime value, CLTV. So the CLTV also some kind of a thing forecasting how much a particular person is going to spend in next 3 years. Of course, it's not a one simple application; it's a combination of things. But forecasting also one of the thing which will work, and price and promotions. Okay, so what particular scenario we need to give discounts? What particular scenario we should not give any discount? What is the calendars? What is the promotions which we need to plan it, and so that your revenue can increase maximum. And a marketing spend optimization. So marketing spend optimization is nothing but way to spend more, way to spend less. Which channel I need to give, which channel I need to spend less. In all the cases, this also something comes under marketing perspective. Of course, sales forecasting, or revenue forecasting, etc. And sometimes operations, and these are all our operations perspective only. And of course, even risk, loss forecasting, right? Or how much losses we are going to do, and cash flows management, right? So like this, you may see a lot of scenarios. You can, you can manage a different type of business problems with the help of forecasting. So are you clear till now? Any questions? I think you understand what is the cash flow management, right? So that means how much cash flows, will, how much incoming, how much outgoing, how much money I should have it to manage my operations well, right? So these are something like, cash flows means liquidity management and liquid funds. How much you may have a lot of assets, but you may not have a cash, liquid amount to manage your operations. Just like a Kingfisher, they may have a lot of assets, but they don't have a cash. Similarly, I&LFS, there is an infrastructure company, which is a government company. They have a lot of assets, but they don't have a cash flows to manage their operations. Similarly, right now it's happening for the Jet Airways. They have a lot of assets, but they are unable to manage their day-to-day operations, right? So this is all comes under risk, how to manage your risk. Okay, so you understand the applications perspective. What is a typical, time series? What is the forecasting? What is the data requirements you have, etc. So typically, you have 3 types of data. One is cross-sectional data. One is time series data. One is panel data. So if you think about a cross-sectional data, what does that mean? So cross-sectional data, in this case, I think till now, whatever we discussed about, like a regression, classification, segment, the examples, whatever we discussed, all the examples we have used cross-sectional data. So what does that mean is the time is fixed. The time is fixed. And the object in this case is varies. What is time is fixed? So let me tell you, the customer ID, you have it, and a customer spend, customer income, customer number of maybe recency or a frequency, or monetary, something like that. So all these are, what are these things tells me that? Okay, customer 1, 2, 3, 4, 5, 6, 7, etc. And you also have a spend, you also have income, you also have this one. This is customers probably fixed time period. Okay, in the last 2 years. In the last 2 years, what is their spend? Last 2 years, what is the average income? Last 2 years, how many times he visited, frequency. Last 6 months, what is the revenue, right? Or a number of items they purchased. So all these are what we are trying to do. We are calculating for a fixed time period. You're calculating a fixed, of course, number of items for purchased in last 3 months, number of items purchased in last 6 months. You can do that. I'm not saying that this one, but that particular variable. Suppose number of items purchased in a last 6 months. So what does that mean? This particular variable across observations, you will use the last 6 months. What is this particular customer purchased? What is this particular customer purchased in last 6 months? So that is what the time is fixed. For a given variable, the time is fixed. So object is varying. What is the object in this case? Each observation is one object. So each, customer 1 is one object, customer 2 is one object. This customer is not same, right? These are two distinct customers, or two, each observation is meant for one customer. So that is what it varies. So if the data is something like this, and this is what we call as a cross-sectional data, most of my customer analytics are, especially regression-based problems, classification problems, segmentation kind of problems. We use this data set because there we are trying to predict customer is good or bad, how much customer is going to spend, or some revenue, or segmenting the customers based on similarity. These are the typical kind of examples which we work. All of them are applications of cross-sectional data. Am I correct or not? So now you understand what do you mean cross-sectional data. Okay, now let's understand time series data. So the time series data is, in this case, time is varies, object is fixed. What do you mean that? Okay, I want to forecast sales for a particular, I want to estimate the demand for a particular product and forecast the demand. Okay, so I'm planning to, okay, for example, cars. Okay, a manufacturer is Maruti, coming up with the model, the existing model itself, like a WagonR. Okay, so the WagonR car, they want to forecast how much demand it has for the next 3 months or next 6 months. Okay, so that kind of scenario, what will you have? The car is fixed. The car is fixed. What we will have? You will have a month, and you will have a sales. And the sales means number of cars sold. Okay, month January 2017, February 2017, March 2017, like this, October 2018. Suppose this is the data you have. Okay, they sold 400 cars here, 300 cars here, 500 cars here, 150 cars here, 290 cars here, something like that. So in this case, what is varying? The time is varying, and object is, for a Maruti car, I'm talking about a particular series. So that is what the time series data. In this case, the time is varies. That means each observation is meant for a fixed time period. That's a month or a week or a year, whatever it is. Right? What is object? Fixed. Object is fixed. So this is what we are calling as a, what is that? It's a time series data. Now let's understand panel data. In the panel data, the object as well as time both varies. And in fact, the panel data is a collection of time series. Okay, so for example, Maruti, they have, for example, 10 models. Okay, now they want to forecast all the 10 models. Like for example, model and a month and the sales, number of cars sold. So what does this mean? model, maybe Alto, January, for example, I have Alto is, they have 15, I mean, it's 3-4 years data you have it. Okay, January 2016. Okay, and February 2016, March 2016, something like that. They have October 2018. Okay, and Breja. Okay, so there is another model, they have it, that is launched recently, maybe 1 year back, or maybe 1.5 year back. So that is what we want is, okay, January 2000 or maybe June 2018, so 2017, July 2017, and like this till they have October 2018, or maybe some other model. Okay, some Wagoner. So Wagoner also is old model, and of course the recent model they got it is something which is automated model. So the automated model launched maybe 6 months back, maybe 7 months back. Okay, then January 2018 and February 2018, March 2018, and so on, October 2018. Of course, in this case you have only 10 months data. In this case you have almost 14-15 months data you have it. In this case almost 50 months data you have it, or maybe 36 months data you have it. Okay, so that means that this is one time series and this is one time series, this is one time series. So like this, if you have a collection of time series in this fashion, this is what we call as a panel data. Now, maybe you might ask me, what is the need of panel data? Because it's just a collection of say time series, right? So sometimes what happened is, for example, assuming that you are a very good customer of Maruti, okay, ideally you are planning to take a Wagoner car, okay, but Maruti launched a new vehicle, and because of the new vehicle, and you bought the new vehicle, you did not buy. So that means that what, some model is affecting the sale of Wagoner. Am I correct or not? So that is, if I want to capture that information, I need to capture the effect of one model on the other. You understand what I'm saying? The effect of one model sale on the other. So if I want to capture these effects, I need to analyze panel data. I can't analyze, individually, and I can't do that, because then you will not able to capture the effect of some other time series with on this time series. Does that make sense? This is very much popular, especially whenever you are doing a price and promotions. Suppose if you are giving a promotion for one product, suppose there are 2 soaps or you have it, okay, so a soap, ideally you are purchasing a 100-gram soap, but their promotion they give as a 200-gram soap, they give a discount of something on the 200-gram soap. So you're supposed to buy 100-gram soap, but you will purchase 200-gram soap. What happened? The effect is changed. Am I right or wrong? So that is what exactly price and promotion scenarios are an effect of one product launching on the other. This kind of scenarios, the panel data is really important. And the panel data, sometimes we also call it as hierarchical data.
Does that mean you analyze all these 3 time series separately and then compare, or somehow you concatenate all, or make all of them together?
I'm saying that make all of them together, just like this is the data I'm going to use.
Okay.
Of course, this is, I was referring that as an example of this one, but yes, this is also we call it hierarchical data. A lot of times, hierarchical data, we have a separate study, hierarchical models. There they will have some fixed effects, random effects, etc. concepts. So I'm not getting into that discussion because this is a little bit, a completely different topic altogether. So as part of our course curriculum, we are not dealing with this one. Just for your info, I'm just giving you the information. What is the panel data? If someone asks you, you should be able to understand what is the panel data means. Right? It's nothing but a time series data only, but a collection of time series, so multiple time series. Okay, so now what I was referring is whenever I want to forecast something. Okay, for example, I have a Maruti Wagoner. We have the data of almost last 1.5 year, and now if I want to forecast for my November, December, January, how can I forecast it? Right? So that is what I'm saying that the forecasting means. Right? So forecasting purpose, we always require to have a data is a time series data. So for a forecasting, we use time series data. Is that clear? So when I say time series data, what is the time series data? I think just now we discussed. What is the time series? So a simple academic way of example, definition is a data, a series of data indexed by time, called as time series data. So in this case, what is my series? My series is cars sold. And what did you do? It's indexing each observation with this particular value, and this is what we called as a indexed by time. Okay, so there are few specification or few characteristics of time series. So first is the data, series should be indexed by time. Series should be indexed by time, and it should be uniform interval. The time interval should be uniform. What does that mean? Okay, so if you have a data, you should have all the data in a monthly basis. If you have the data, all the data should be in a weekly basis. I don't mind what level of granularity you have it, but what we need is all of them should have a uniform intervals. Okay, one observation is for a month and one observation is for a quarter. That will not make sense. Is it clear? So that is the second thing. And we should not have no missings. You should not have missings. What is that? Should not have missings in the data. What does this mean, guys? Yeah. So should not have missings means, okay, even suppose you have a data from January 2017, but some reason your June data in 2017 missing. So you should not have that missings. If there is a missing, probably you need to impute with appropriate value. So missing imputation will be done, but not similar to cross-sectional data. Okay, missing imputation will be done if data having the missings as follows. One is forward filling. One is backward filling. What is a forward filling, backward filling? I mean to say that, okay, suppose the data you have January 2017 to till October 2018, but June 2017 missing is there. And that kind of situation, what happened? You already know that first 5 months data, January, February, March till May. So using that 5 months data, fill it for June. So that is what forward filling. Backward filling means the reverse. Okay, suppose you have the data, only January 2017 to October 2018, but you don't. I mean, there is a variable is missing in February 2017 or maybe March 2017. So now what happened? You don't have too many data points in the first before, and then that kind of situations we will make use of March April to that data, and we will try to fill it with the some value. And here is the place, some kind of a moving average concept. We will discuss about that, what is moving average, etc. So very typically we use moving average, to fill the missings. Or a moving average, weighted moving average. There are so many different ways. Or maybe sometimes we will use centered moving average, etc. So typically the missing imputation will be done with the help of the averages, but not a normal average. This is a moving average. Okay, so that is the first and important. And one more important thing is my current value. Okay, so I mean to say that the future trend and similar to past trend. So this is the one of the key assumption. What I'm saying is, okay, whatever the data you have it, whatever the patterns you are identifying, the pattern will be applicable to future also, right? So this is a key assumption. Based on this only the predictive modeling works, especially the forecasting works. Okay, but assuming that last 3 years, you have one pattern, but because of some reason, completely the patterns got changed. So that is not applicable. In that kind of scenario, you will not able to use the time series. A just simple example, consider what is that recession time in 2008, 2009. That is the time period is recession time. What happened? Because of the recession, some companies are doing really good, but because of this recession and a lot of constraints, etc., the company trend got changed. Earlier it was exponentially growing, but after that it's growing as a little less. Now what happened? Because of the recession, that particular year is changed the completely pattern of the data. So that kind of situation I cannot use before recession and after recession data combined together, come up with a forecasting model. Does that make sense? Yeah. So this is what I mean to say, that the trend, if some reason it's getting changed, it is if you use that data, you're not able to come up with a best model, right? So that is what, if that kind of thing you see, that you need to adjust. Clear? Okay, these are the key characteristics of time series case. Yes, Prerana.
So what will you do in this kind of a situation if
So in that kind of scenario, what we will do is you will remove the data before recession and you will use only the data after recession. That is one method. The other method is by keeping the factor of recession, you will adjust your time series from the existing data. That is a little bit business understanding, industry understanding, something is required.
So I mean this kind of a scenario can be very common, right? In case of a market event or a launch of new drug.
Yes, that is what you should know. What is that event, and based on that event, you need to adjust accordingly.
Okay.
Some of the small events, basically, you can keep that as a effect. That effect is basically you can consider as one of the independent variable. We'll talk about that, and that some of these things you can adjust by introducing the new variables in the data. But some of the things which you can't adjust, and that kind of recession kind of a thing, you can't really adjust. Okay, so what you can do is you can take after recession data for forecasting purpose.
Okay. Okay, thank you.
Kerala floods. Yes.
So whatever they had data, affected by Kerala floods, everything
Yes, that is the kind of scenario. What we will do is that particular event, after that particular event, we will keep one kind of some dummy variable introducing as part of the data, and that will some extent capture the effect of that floods or this kind of events. Right? We'll see that part. But if I'm talking about a time series, this is the characteristic you should have it. If you don't have these characteristics, you need to adjust the data. Make sense? Okay, now you understand what is the time series, what is the applications of time series, what is the different types of data, and what are the key characteristics of time series. Okay, now what I want to talk about, whenever we are talking about a forecasting, I want to introduce few terminology. What is the few terminology? Let me tell you. So of course we discussed about time series. We discussed about forecasting. This already we discussed, and there are a couple of things like lag, lead, difference. Okay, and these are the few things, and autocorrelation, partial autocorrelation, autocorrelation extension is autocorrelation function, partial autocorrelation function, and autoregression. Okay, and of course, we also call it as a time series components. We will discuss about what is the time series components. In that, there are components like trend, seasonality, cyclicality, or irregular component, and these are the things. And the other thing is, a time series characteristics perspective. We have white noise, a random walk, and the series is stationary, right? So these are some of the terminology related to forecasting. So
White noise comes from which category?
sorry,
White noise.
I mean, sometimes we will call it as a series is white noise, a series is a random walk, a series is stationary. What are that means? That's what we are talking about. And some tests we also have, ADF, augmented dickey-Fuller test. And when we said trend, the opposite is detrending, deseasonalization, and what is that? Detrending, deseasonalization, and decomposition. I mean, this is also called as a seasonal decomposition. And we also, there are a few more terms. Okay, in the decomposition also, we have additive decomposition and multiplicative decomposition. And this is also, we call it as a unit root test. And the metrics perspective, like MAPE, RMSE, MSE, and techniques perspective, moving average, weighted moving average, centered moving average, ETS models, or we also call it as whole to winter methods, also called as a exponential smoothing, and ARIMA family, and AR, MA, ARMA, ARIMA, SARIMA, Arimax, SARIMAX. Okay, and of course, time series perspective, univariate time series, univariate time series, and multivariate time series. Okay, so these are the few terminologies which you really require to understand, guys. Okay, so whenever we are using a forecasting, if you're familiar with this terminology, you can understand any paper, any book, anything related to forecasting or any blog. Okay, so now let's understand, I think these two terms which we discussed already, and I think the univariate time series and multivariate time series, let me explain that. So for example, you have a particular product, like I told you, a Wagoner car. Okay, you already have a monthly sales. You want to forecast next demand for Wagoner car in next 6 months. Okay, number of cars sold. Okay, month 1, month 2, month 3, month 4, month 5, like this. You have a 30 months data, and here 300 cars, 200 cars, 150 cars, 190 cars, 320 cars, 150 cars, 200 cars, etc. And you also know that this sale, car sales also depending on the some kind of a marketing spend. So in the marketing spend on the TV, for example, okay, so 20,000, maybe a 15,000, 2,000, 5,000, 10,000, 13,000, and 3,000, or maybe 30,000. And the marketing spend on some discounts, because sometimes they will give discounts. They are giving a high, discount here, 10%, here 5%, here 0%, here 0%, and here 3%, and here 2%, here 10%, something like that. So basically, do you think is the sales is depending on these variables also? Because right, the amount of discount you given, what is the sales, and the number marketing spend on the TV, that's also can affect your sales, right? So this is what, if I take only one series, this is what we call the univariate time series. If you took all of them, these are 3 series are there indexed by time. What is the 3 series? Cars sold, and amount spent in each month, and percentage discount you given in each month, right? So this is what we called as a multivariate time series. So I mean to say that this is an example of a multivariate time series. This is an example of univariate time series. This is univariate. This is a multivariate. Okay, so are you clear on these terms? Okay, so this is what we call it as a univariate time series and multivariate terms. So let's understand these 3 terms. So these 3 terms are, for example, if you take this series, okay, so lag is nothing but lag 1 cars sold. So what does that mean? The 1 month lag. So this is the lag 1. So the current month data is past month in. Lag 2. What is that? Lag 2 means, lag of lag, or maybe a 2 months before. A lot of times what we do is, for example, a simple example is, if you think about this one, if I take a marketing spend TV, lag 1, so lag 1 is this one. So a lot of times what happened is, my current month sales is depending on the previous month marketing spend. Sometimes that is possible, because sometimes the spend, whatever you did on the marketing, it may not give impact immediately. It may give impact in some time. So that kind of situation, this lag variables will be very helpful. Correct? So this is the kind of scenario, the lags will be very helpful. And what about lead? Lead 1 number of costs. Lead is nothing but my future value will be my current value. So what situations this can be very helpful is, for example, budget. Every budget happens in the March. Or maybe a government is taking a decision in a 1 month advance, and that will implement after 1 month. So whatever the decision you are taking, and that itself will impact your sales. The decision will impact your sales. So that is what exactly we are calling as a lead. So the future decision sometimes impact my current month sales. For example, in a budget, they announce a 10% rate cut on washing machines. Will you buy current in this month the washing machine? No, right? So that kind of situation, the future decision, the implemented that will be implemented in April or March or April onwards, but you will not buy in this month. Festivals that comes under seasonality. But here I'm not talking about seasonality. I'm talking about some kind of a decisions which you are taking future implementation, but that will impact your current month sales. So that's the kind of situation this lead where, of course, very rare scenarios we think about this one, but generally, lags will be very helpful. So now you understand what is the difference. What is the normal time series? What is the lag of time series? What is the lead of time series? Of course, lead one, lead two, of course, as many as. If there's no, I'm just giving an example of lead one, lead two. What is that lead one, lead two means? This is what it means. Okay, now difference of series. A difference of series is nothing but my actual, current value minus my previous value. That's same as your current value minus my lag value, lag one. So that is what we call it as a difference. And difference two, of course, that is nothing but difference of different series. This minus this. Okay, this is what we call it as a difference of time series. So are you able to follow me? What is the lag, what is the lead, and what is the difference of time series? What does this means? Are you clear or not? Okay.
Can you just show
the
us
difference is sometimes difference two is nothing but difference of difference. So this is basically this minus this.
I see. Okay.
What is the use? Is the use for a typical difference is a lot of times we'll convert a non-stationary series into stationary series by differencing the series. We'll tell you what is the need of this one. A lot of times the model, whenever you are doing a forecasting models, one of the prerequisites is the series should be stationary. Okay, so we will talk about this one, but at this point of time, understand what is a term means. Okay, now let's understand this part, this section. So whenever we are talking about a time series, suppose the 300 cost sales. Okay, so 300 sales, it could be because of, last month sales is high and this month's also sales is high, and overall market is growing. So because of the trend, you're also seeing some increment on the sales. That is, we are calling as a trend. Trend is nothing but what? Over the time, there is a increase. Over the time, there is an increase. And in between, irrespective of small fluctuations in the series. So what does that mean? So for example, let's understand this. So if you look at a series something like this, suppose this is x-axis, this is y-axis, and you have some kind of a time series like this. Okay, so if you look at, there are small fluctuations, either increasing, decreasing, etc. But over the time, what happened? You see that there is a trend. The trend is it's increasing trend. So this is what we call as a positive trend. Positive trend means over the time it's increasing, and over the time it's decreasing. For example, something like this. And this is what we call as a negative trend. You understand what does that mean, positive trend, and what is the negative trend? The trend is nothing but over the period of time it's increasing, and over the period of time it's decreasing. And the types of trend is, one is a positive trend, one is a negative trend. There is no trend means there is no, it will be a flat, right? And the second thing is seasonality. What is seasonality? I mean, you mentioned that in a particular time periods, you see there is a high sales. Like for example, every December, you see that there is a high sale in apparels. High sales in ACs and fans. Yeah, there is a peak demand in peak demand for electricity, right? So these are all something related to examples of seasonality. But the seasonality is basically when we are comparing two time periods within the, time periods less than a year, less than or equal to year. So what does that mean? Suppose if I compare year 1 versus year 2. Okay, this is my data I have in a monthly basis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So if I compare year 1 and I see that there is a very high sale in June in both the years. There is a very low sale in October. There is a very low sale in January in both the years. So that means that both are having some kind of seasonal impact. What is seasonal impact? In those particular months, I'm observing that there is a low sales. Or in that particular months, I'm seeing there is a high sales. This is also applicable to, instead of taking months, I'm also taking my data is in a weekly, for example. What happened? In a particular weeks, I'm saying there is a peaks. In a particular weeks, there is a slumps. Or suppose the data I have in daily basis. Now what happened? Probably you see that in the weekdays there is a high demand, or weekends there is a low demand, or vice versa. Or if the data you have in hourly basis, you can see that in the morning, in the evening, in the afternoon, do you see any kind of a change? So that's the kind of situation. What we can do, we can compare. Suppose if the data is in hourly basis, what is the comparison I can do? I can do year 1 versus year 2. I can do, least granularity is a day versus day 2. That every day, and weekends versus week, and weekends, in the weekends, I mean to say that I'm talking about, I'm talking about year 1 and year 2. So in that year 1, on the same day, the same day means, okay, last year, January 1st, and this year, January 1st. And last year, 50th weekend, this year, 50th weekend. Or maybe a month-on-month comparison, okay, January to February, quarter-on-quarter. So quarterly comparisons. Quarter 1 versus quarter 2. Month 1 versus month 2. Or, like this, can you compare a different level of granularity? You know, the comparison is day 1 and day 2. So that means that if I compare across days, the pattern is similar. For example, if the data is an hourly basis, assuming that this is electricity demand, I'm observing that every day I'm seeing that there is a demand very high in the evening, especially 6 to 8. Between 6 and 8, there is a high demand. Now what will you do? That means that there is a seasonality in that particular period of time. And I'm observing that every day there is a demand is high, but especially in the weekends, there is much more demand. In the weekends, I'm seeing that the demand is high across the day. And if I look at, if I compare month 1 versus month 2, every month, especially the week 1 and week 2 is very high demand, and week 3, week 4 is less demand. Or if I compare with the months, months especially, January and February I have low demand, but April, May, June, July is a high demand. Okay, so do you think the granularity of data will also influence what type of seasonality? The seasonality can have on a daily basis, weekly basis, hourly basis, monthly basis, whatever level of granularity you have it. If the data you have it, a monthly data, you can look at the comparison between month and quarter. Month and quarter. If the data at a weekly level, week, month, quarter, you can do that. Right? So that is what the seasonality means. So seasonality means the patterns will be similar for a time period. So like when you are comparing words, year 1 versus year 2, or a month 1 versus month 2. So that is the kind of situation we call as seasonality. So the seasonality, like movie tickets demand. So you know that movie tickets, will be very high demand, especially in the in the weekends. In the weekdays, it will be low. Even within the day, in the morning will be low, and the evening will be high. Don't you agree with me? So that's how they will also change their pricing. You know that? In the weekends, the same ticket is 300 rupees. The same hall, same movie, same theaters, everything is same. But you are paying 300 rupees. The same movie ticket, you will also get it on the weekdays, with the 150 rupees. Even within the day, in the morning 100 rupees, in the evening 150 rupees. Do you agree with me or not? So that is what the seasonality is. And now let's understand cyclicity. What is cyclicity? Cyclicity is similar to seasonality, but the time period comparison is more than 1 year. The time period comparison is more than 1 year. A simple example is in a World Cup. World Cup, when it will come, every 3 years or every 4 years, whatever it is, depends on the game. Okay, assuming that a World Cup of maybe cricket World Cup, it comes every 4 years. So you might see a certain products have high demand in that particular every 4 years. You might see there is an increase. Or maybe a simple example is the usage of watching TV. At the time of World Cup, you may watch more. Am I correct or not? And maybe at the DTH, the consumption will be more in that time, or your power consumption will be more on that time. So that is what we call it the cyclicity. Do you agree with me? Cyclicity, seasonality is a similar, but the pattern repeats more than 1 year, and that is what cyclicity is. Of course, first identifying a pattern of cyclicity required more amount of data. But seasonality identification, at least you should have a 2 years data. Then only you can identify the seasonality. And the other, whatever the component which you don't have any pattern, that is what we call as a irregular component. That is what we call as a irregular component. So the trend tells me that on an average, every month, what is the net increase you see that. That is what trend. And the seasonality means the time period, how much is affecting or how much is contributing. That is what we call as a seasonal component. And cyclical component means it is similar to seasonal component, but the cyclical component is more talking about how much that particular cyclical component is contributing to my sales. Whatever left over, that is what we call as a irregular component. So that means that whenever I have a time series like this, so this time series is basically assuming that this is a YT. YT is nothing but cost. So why I'm saying that T is an index. Okay, Y1 is nothing but month 1 sales. Y2 is nothing but month 2 sales. Y3 is nothing but month 3 sales, etc. That is what YT means. So the YT, can be splitted into, assuming that my trend contribution is TT and my seasonal contribution ST, my cyclical contribution CT, and my irregular contribution IT. Suppose if I'm able to split this 300 into different components, this is what we call as a multiplicative decomposition. Multiplicative decomposition. And the same thing if you are splitting TT plus ST plus CT plus IT. And this is what we call it as the additive decomposition. So assuming that, assuming that the trend component on an average every year, every month, it's contributing, for example, 50 or maybe 150 is contribution coming from the trend. So irrespective whether whatever season you have it, whatever not season you have it, you see that some kind of a trend. So first month you're getting 150, maybe second month is 160, third month is 170, something like that, assuming that. And the seasonal component. So ideally this trend component this much, but the seasonal component, that particular season, that particular month, you might have a high sales, you might have a low sales. Okay, this is contributing a 1.8 times. That means that if the sale is generally 150, but it is contributing 1.8 times of sales. That means that approximately 270 or 280, whatever it is. Is it correct? And whatever of course, right now I'm not worrying about the CT because CT required more data. IT, what is the IT left over this? 300 by this multiplied with this. So this is what a irregular component. If you look at all three multiplication, what we'll get it? This 300. So if I'm able to split my series into these components, this is what we called as a decomposition. The decompositions are two types. One is additive decomposition, one is a multiplicative decomposition.
Chandra, can you please repeat the last thing you did?
I mean, I'm saying that if I want to split this thing, there is a component which I'm getting from the trend. And there is a particular, ideally we're supposed to get a sale of 150 based on the trend, but in the January, I'm seeing there is a high sales. So how much that sales is contributing in a January month, this is this much amount of contribution you are getting. And whatever leftover, that is leftover is if I want to come up with this kind of a decomposition, that means this into this should be this one. That means whatever leftover is, this divided by these two will be this part. And this is, if I'm able to split your YT into these components, this is what we call it as a multiplicative decomposition in this case. Are you able to follow me? So that means how much is contribution is coming from different components. So this is what time series components, and this is what we call it as a decomposition. And why do we need decomposition? I will discuss about that, because at the end of the day, if a data is there, if a component is coming from seasonal effect, that I want to remove that seasonality part out of that. That means that, and that is what a deseasonalization. What is deseasonalization? Removing the effect of seasonality from the data. This is what we call it as a deseasonalization or adjusting seasonality. Detrending means removing the effect of trend from the data. This is what we call it as a detrend. So are you clear with the terminology? What is a decomposition? What is a deseasonalization? What is a detrending? What is a additive decomposition? What is a multiplicative decomposition? Are clear with the terminology? Okay, these are the terminology related to decomposition. Where did I mention? Yeah, here. Okay, now let's understand these terminologies. Okay, so let's understand what is this terminology is. Suppose you have a data month. Okay, now what is autocorrelation? So what is autocorrelation? Autocorrelation is nothing but self-correlation. What do you mean self-correlation? So correlation is nothing but what? It's a linear relationship between two variables, right? But when you have autocorrelation, I'm saying that I have only one variable, but where I can talk about autocorrelation. So this is the place. Suppose you have YT and you have lag1 YT and lag2 YT. You can create lag3 YT, etc. Will you be able to create or not? So if I take a correlation between YT and lag1 YT, correlation between YT and lag2 YT, and correlation between YT, lag3 YT, and so on. So if I take this one, so what is indirectly tells me that? Okay, let me explain this one. Suppose you have 30, 40, 20, 1, 15, 25, 40, 35, 56, etc. Okay, this is month 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. What is the lag? This is previous one. And lag of lag, lag2. So when I look at the correlation between YT and YT, lag1 YT, what does that mean? You are identifying the relationship between these two. Okay, leave it the first observation. The remaining observation, if I look at the correlation between this one, this is same as can I say that correlation between your YT and YT minus 1? Correct or not? So that means that a relationship between my current value and my previous value. YT minus 1 is nothing but previous value. And this is nothing but, can I say that the correlation between YT and YT minus 2? Lag2 is nothing but, this one and this one, you are looking at the relationship. That is nothing but this one and this one is same. So can I say that this one is same as a YT and YT minus 3? So this is what we call as autocorrelation. So autocorrelation is nothing but your current value and the previous value is there any relationship or not. That's what we are looking at. And suppose if you are getting a autocorrelation is suppose like this 0.3, 0.7, 0.2. So what is this means? Tells me that my current value having a strong relationship with the previous to previous value. Previous to previous value. Am I correct or not? Lag2, you are saying that there is a very strong relationship between correlation between YT and lag2 YT. That is nothing but correlation between YT and YT minus 2. So indirectly nothing but what? Your 2 months before value is influencing your current month's this one. And this is what we called as a autocorrelation. I mean, this is what we call as autocorrelation. And the values which we are capturing, this is what we call as an ACF. What is ACF? Autocorrelation function. Autocorrelation function means how your current value is having a relationship with the previous values. You are looking at lags. Okay, current value YT and lag 1, YT and lag 2, YT and lag 3, YT and lag 4, YT and lag 5, etc. And if I capture those values, and that is what we call the ACF. So by looking at the ACF, what can you identify? By looking at the ACF, what we can identify? My current value, is there any relationship between your current value with previous values or not? If all the values are close to 0, for example, if all the values are close to 0, what does that mean? Can you say that is there any relationship between your current value and the previous values? That means that you are unable to identify from the existing data. You cannot do the forecast for future. If there is no relationship, how will you forecast it? So if there is no relationship, between current and the previous values, and that series called as white noise or random walk. So if ACF is almost close to 0, if ACF is with every lag, it's almost close to 0, and then we can say that that series is not used for any kind of forecasting. That is what we call as a random walk, or that is what we call as a white noise. So is this clear? What is ACF and what is white noise? What is the random walk? The terms are clear?
So Chandra, this is same as what you said initially in the key assumption, that if we do not have, the previous trend is not matching, then we cannot do the forecast.
Correct, exactly.
Chandra, can you just explain white noise once more time?
Now, white noise is, I'm saying that if I'm looking at this one, what is the correlation between your YT and lag 1 YT? What does that mean? It's a relationship identifying between your current value and the previous value. What about this one? It's a current value and the previous to previous value, and current value and previous to previous value. So that means it's the lags are increasing. That is nothing but, suppose if all the relationship is almost 0, that means there is no relationship between your current value and your past values. That means that you cannot really identify any relationship between your current value and previous values. And if all of them close to 0, then that series we called as a white noise or a random walk. Is that clear?
Yeah, you also told that if the data is having the white noise, this data cannot be used for forecasting, right?
Yes, correct, exactly. So what the data is having white noise is not correct term. If series is a white noise, okay. So if there is no pattern in the data, that is what we call it as a white noise. If the series is white noise, then that is not used for forecasting. We cannot really come up with any kind of a model.
Okay. So I have one doubt. Suppose you're talking about lag 1, lag 2, lag 3. Okay. And if the last lag have certain kind of relationship between the data, so that particular data is not a white noise data, right?
If there is a relationship, that means that the data is not a white noise. That is a time series.
Yes. I'm talking about at any lag. If there is a
yes, at least one lag you should have it. That's what I said. If all the lags are close to 0, then only we can say that it's white noise. If even first 5-6 lags you did not have it, but in one lag you have something, and after that you don't have any lags. After that, any lags also you don't have a good correlation. Still, I will call it as a time series is not a white noise, because at least with one lag you are seeing some relationship.
Okay, got it. Thanks.
Okay, cool. So this is the white noise. And now there is another term called PACF. Okay, so let's understand this term a little bit better. Okay, if you look at the correlation between YT and YT minus 1 is 0.3, and YT and YT minus 2 is 0.7, and YT and YT minus 3 is some 0.2. Suppose if there is a relationship between YT and YT minus 1, that means that there is a relationship between YT minus 1 and YT minus 2. This is same as a correlation between my YT minus 1 and YT minus 2. Of course, this is not the same, but I'm saying that this is also applicable, right? So that means that if I want to look at the relationship between YT and YT minus 1, just a contribution of YT minus 1, I need to remove the impact of YT minus 2 on YT minus 1. So what indirectly I'm saying is, if correlation between YT and YT minus, assuming that there is a relationship between your current value and previous value. So that means that the previous value and previous to previous value, there is a relationship. So that is what I'm saying, that there is a relationship between your YT minus 1 and YT minus 2. So that means that a YT minus 2 also influence my YT, and YT minus 2 also influence on YT minus 1.
So this is in month. How is it related?
No, it is related. I mean to say that's what the lag I'm talking about, right?
That is 1 month behind. But how can we see that YT minus 1 is related to YT minus 2?
See, my current month sale is depending on the previous month sale. Okay, my previous month sale is depending on the previous to previous month sales. That's possible or not? So that means that if I want to see really the influence of only the last month's sale, that means I need to remove the impact of the previous to previous month sales. Okay, a simple example. I'm giving a TV advertisement in the last month, previous month. I mean, from January I'm giving, February I'm giving, March also I'm giving. So if I'm looking at my sales, the sale is impacting based on the current month. The sale is impacting previous month. The sale is also impacting by previous to previous month. Am I correct or not? For example, you seen the advertisement 2 months back, but still you remember that advertisement and you bought it in this month. That's much possible, right? And some person bought it, the item because they seen advertisement last month. So in that kind of scenario, if I want to see the net impact of last month's sale, I need to remove the impact of my current month, and I need to remove the impact of previous months also. Correct or not? So if I want to capture that kind of a thing, that is what we call as a partial autocorrelation function. What is a partial autocorrelation? You are looking for a relationship between YT and YT minus 1 after removing the impact of YT minus 2, YT minus 3, YT minus 4, etc. Is that clear? So that is what we call it as a partial autocorrelation. Are you guys able to follow me? So the partial autocorrelation.
One question, do you do the same here? You're doing YT and YT minus 1. Do you do the same thing for YT and YT minus 2 while removing YT minus 1, for example?
See, I'm just explaining the concept of the partial correlation function. I'm just explaining that one. So you don't need to do separately. That is a partial autocorrelation function itself will taken care of that. But just for your info, what I'm saying is, if there is a relationship between my current month sale and previous month sale, the previous month sale is also influenced by my previous to previous month sales. That means that there is some impact of YT minus 2 on YT. But I want to capture only the impact of YT and YT minus 1. So that means that I need to remove the impact of YT minus 1, YT minus 2, YT minus 3, YT minus 4, etc.
Okay.
By removing that effects, and I'm just capturing the impact of yt minus 1, and that is what we call as a partial autocorrelation. Is it clear?
Yeah.
So we will see that what is the use case of what situations we use the ACF and PSF in the little later point of time. But at this point of time, if you understand, these are the terminologies which I was talking about. And you might also seen that, this discussion about the white noise and random walk I already discussed. And there is another term which is a very interesting term, which is called stationary. So series is stationary. A series is stationary. Suppose a series, when can we say that the series is stationary is, for example, if you look at, this is the x-axis is the time period and y-axis is the sales. And if I have some kind of a series like this, so do you see that there is a trend in this? Okay, so that is you have the trend, and probably you might see the patterns are almost similar. I mean, the pattern is here to here and here to here. It is similar. That it's indicating what? Seasonality, because every 3 months or every 4 months that's repeating the pattern. So that is the, I mean, in this data have both seasonality and trend. Okay. When can we say that the series is stationary is a series over the time you should have a constant mean and a constant variance. What does that mean? So, okay, if I take first 3 months time period and the second 3 months time period, if you look at the average over here and the average over here, it will be different. So, am I correct or not? On an average for this time period, maybe it have a 200, and you might have a here more than 200, maybe 250. And here the average for the third time period, you might have a higher average. So in this case, is the mean is constant over the time? No, right? So, and then you can say that the series is not stationary. So what I'm saying is a series is stationary. That means that over the time, you should have a constant mean and a constant variance. So what do you mean constant variance? Suppose assuming that you have the data like this, and the data is influencing like this. Suppose if I look at this one, if you look at, is the data having a constant variance? No, right? Because sometimes you have a lot of big peaks and sometimes you have a small peak. Suppose if you look at this data and the variance is somewhere, for this time period, you might see variance is a little low. But in this time period, you see that the variance is high. Variance means the fluctuations which you are observing there. So that is what we call as a non-constant variance over the time. So if I look at the series something like this, so let me show you. Suppose, suppose if the data is something like this. So assuming that this is a series, if you see that the mean is constant over the time, correct or not? Correct or not? And the variance also, the values is always fluctuating within the values of this one. This is an example of a series is having a constant mean and a constant variance. If the series is having a constant mean and constant variance over the time, and that series we call it as a stationary series. There is no trend. Of course, seasonality is there, but the seasonality is, it's a kind of a, I mean, it is the pattern is repeating same. Is that clear? So this is what a series is stationary. And a lot of times, I told you the stationarity is the prerequisite for forecasting models. So a lot of times, many forecasting models many forecasting model, the prerequisite is stationarity. Okay, if series is stationary, there is no problem. But if series is not stationary, what we need to do? So this is what exactly we need to convert. I mean, you remember in a linear regression, if my y is not following a normal distribution, what we do? We convert y variable by applying some transformation in such a way that the transformed variable follows a normal distribution. And similarly here, if series is not stationary, we will convert a non-stationary series into stationary series. So how will you convert? You know, this is a place, there are multiple approaches we have it. One common approach is by applying a log transformation and detrending, deseasonalizing, and differencing the series. Okay, so these are the common approaches, or sometimes we use a combination of the approaches, you know, to convert a non-stationary series into stationary series. If the series is having a non-constant variance, applying a log transformation will be very helpful. If the series is not having a constant variance, in that kind of situation, the log transformation can be helpful. If the data having a trend, if the data having a seasonality, you may remove that peaks and you may remove that trend component, and so that the series can be a seasonality. And applying the difference of series. You remember how to do the differencing? And that is the another way to convert a non-stationary series into stationary series. So very commonly we use these two things, because when you do the differencing, in a lot of times you are taking care of the trending, removing the trend and removing the seasonality also. So that's the reason most of the times we apply log and differencing the series to convert a non-stationary series into stationary series.
Chandra.
Yeah.
Can we use lag also to convert non-stationary to stationary data?
Differencing is nothing but only that only, right? So differencing is nothing but actual minus lag of series.
Okay.
You remember, I was explaining that differencing the series, diff1, diff2, if you remember, the diff1.
You did differencing whenever you are taking the lag, and after that we have done the differencing. Lag means I want to say y minus t.
Correct. Yt minus 1. Yes, yt minus 1.
This is the lag. The differencing is something different you have just explained.
No. Differencing is basically diff1 is, let me tell you, diff1 of series, yt is, this is same as a yt minus lag 1 yt. So this is a one, that is the same as yt minus 1.
Okay, got it. Okay, thank you, got it.
So are you clear now? Okay, so how to check a series is stationary or not? So you remember, how did we check as a particular variable is following a normal distribution or not? By looking at the graph, histogram, and by also doing some kind of a test called Durbin-Watson test, etc. Of course, we did not do the test, but that is the one approach. Here also, we can also use graph and to identify series is stationary or not. And the other one is, there is a test called ADF test. This is also called as a unit root test. This is also called as a augmented Dickey-Puller test. So what is this test tells me that is, in this case my null hypothesis is the series is not stationary. An alternate hypothesis is the series is stationary. So by looking at the test results, what can you say that? How can we conclude whether series is stationary or not? If my p-value less than 0.05, then we can say that series is stationary. So perform ADF test, look at the p-value. If the p-value less than 0.05, I can say that series is stationary. So this is the another approach to identify whether series is stationary or not. Or over the time, calculate average and variance and compare they are similar or not. Okay, if the data you have monthly data, maybe every 3 months now you can calculate the averages and see that the averages are similar or not. So like this, you may think about different approaches. Of course, most commonly we use this one. Of course, by looking at the graph also you can say that, but most commonly is this is the test which is help you to whether series is stationary or not. If series is not stationary, probably you can use one of the above method and convert it. Clear? So now you are clear with this term stationarity and the ADF, unit root test, and all of these things. Now let me explain these terms, and before that, do you want to take a break?
Chandra, I have a question.
Yeah.
So Chandra, you said that white noise and random walk are same thing.
White noise and
random walk is same thing.
Yes, and in terms of the terminology to understand is same thing, but in the definition there might be a slight difference, but don't get confused around that. So at this point of time, white noise and random walk, I'm using a similar.
Okay, and for the null hypothesis you just said, so I mean we assume that series is not stationary is the null hypothesis, is it?
That is the test which is they created, that defined it. Yes.
Okay. Thank you. Because null hypothesis we always check for equality.
What we are rejecting basically.
Okay.
You're rejecting null hypothesis if p-value is low, right?
Yes.
That's what we are trying to do.
Okay.
Okay, so the mathematics behind that. So basically, this is derived out of some mathematics. So I did not get into the discussion because if I need to prove that theorem, it will take my another 2 classes. So I'm not trying to prove that theorem, but this is the theorem, we have it. Of course, this concept is derived from some unit root test and some concepts around that. So I'm not getting to the discussion, but yes, if you want to go back and see that, they will, either you can check ADF test. That ADF test is, people call it as a unit root test. So now you need to understand what is unit root test and all of these things. If you want to look, derive the how, what is the null hypothesis, how did you derive the null hypothesis, etc. But we don't need to really worry about the mathematics behind that at this point of time. If you think about, what is my null hypothesis, what is my alternate hypothesis, anyway, my system will give you the results. My system will give you what is the p-value. If the p-value is low or not, then you check it and reject the null hypothesis. Okay, so now, assuming that I have some kind of a data, okay, some kind of a data I have it. Now I'm forecasted. I forecasted means, for example, I come up with some kind of a model and I can say that, okay, assuming that I have this data and I want to, for example, 50, 20, something like that. And you use the data for 6 months and you build a model and you want to forecast for next 3 months, and for next 3 months I already have a values, for example. Now you forecast it as this is a 59 and this is a 49 and this is a 15. So this is your forecasted values, and you build the model based on this time period and you forecasted this one. Now how can we calculate the accuracy? So what is the accuracy? The accuracy perspective, just like this is actual and predicted, and you know the regression, how will you accuracy checks? You can do that. Like in accuracy checks for a regression problem, what did we do? Mean absolute percentage error, RMSE, MSE, etc. Right? In a similar same terminology, I'm also going to use it there here also. So here I may have actual value, I have a forecasted value. Now I can calculate the actual minus forecast, that is error, take the absolute, take the percentage, and I take the average of those percentages. That is what we call as the mean absolute percentage error. Or error, square it and take the mean, that is what mean squared error, and root mean squared error. So these terms, I think we already discussed in the regression. So the concepts are same. I'm not worrying about that metrics, because we already discussed in the regression problem. Okay, guys, these are the foundations really required for a terminology perspective. Now, what we need to do? If I have a forecasting, data, for a time series data, now I need to use some kind of a technique to solve the problem. That means I need to use some technique to come up with the forecasted value for future. So that's the place we have a different techniques. So in this, out of these techniques we call it as a basic techniques, and these are a little bit advanced techniques. Maybe little very advanced techniques. There are some more like ARTS, GARTS, and vector autoregressive models, wavelets, etc. Of course, as part of our course, we are not covering this part, the very advanced part. And I also told you, very advanced is maybe the hierarchical models. We are not covering these things. So we will cover till this first three things. And in the basics also, in the moving average, weighted moving average, center moving average, we don't use this as a technique, because these techniques are not very efficient in terms of the accuracy. But the data size is very small, and that kind of situations we use. But these techniques mostly we use as an intermediary techniques. Like as I said, that one is missing imputation perspective, or identifying the trend perspective, right? And identifying some kind of a seasonal component perspective. So this kind of situations we use these moving average, weighted moving average, but we don't really use as a technique to forecast. Okay, so having a knowledge of the concept is important. But sometimes we use these techniques to forecast models, and otherwise these are the very common way of using the techniques like ARIMA family. And one more thing I also did not tell you, even you can also use a regression, a normal regression, to come up with the forecasting. Okay,
Chandra, one question.
Yeah,
I think do we cover, like, if the data having any missing value, should we use those data in forecasting?
so I already told you, if you have the data is missing, I told you will use one of the method like moving average or weighted moving average to impute the missing values. But most of the times its imputation is not based on the technique, we don't use it. Of course, we use technique if you don't have any business knowledge, but if you have for this kind of situations, you really require a business understanding. So a lot of times we discuss with the business and we will impute the values, what is the corresponding missing.
So I have done a moving average, but I never did missing value imputation with the help of a moving average. So I am requesting, can you just whenever you are going to do the example, just show me how can we impute missing value with the help of a moving average.
Sure, I will do that. Yeah.
Okay, thank you.
Any questions till now? Okay, so now what we'll do is let's take a quick break. Once we come back from that, we will go one by one, technique, and then we will, implement them in Python. Okay, so it's 11:51. By 12:05 we should be here. Okay, so now let's quickly understand the techniques what I was referring. So for this, first of all, understand what are these moving average weighted moving average and the centered moving average. Suppose you have the data of monthly sales, and the sales you have it, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So maybe consider as a quarterly data, and 300, 200. Okay, you have the data like this. Now, what is moving average? So moving average is nothing but, when we are taking the normal average, what is the normal average? Just taking the average of these values. Right? This is a simple average, correct? This is a simple average. Moving average is nothing but average over the time. So when I say average over the time, how many periods we need to take average? So this is the place, suppose moving average is 4. That is nothing but what? The moving average of 4 time periods. What does that mean? You are taking the average of last 4 time periods. This is what we call it as a moving average 4. Moving average 3 means taking the average of last 3 time periods. So of course, in this case, if I extend this one, what does this mean? What does this mean? This is a moving average of these 4 time periods. This is a moving average of last 4 time periods. This is a moving average of last 4 periods. So basically, over the time, the number of time periods will be same, but the only thing is the period will be the same, but the number of past periods will change. So number of past period will be the same. I mean, this is, if you are looking for this one, you are taking the last 4 time period from here. So this is what moving average. So, and if I take a moving average 3, average of last 3 time periods. This is what we call it as a moving average of 3. Is it clear? So now, in case if I take this one, this is a moving average 3, moving average 4, etc. So what are weighted moving average? Weighted moving average is, for example, weighted moving average 3. So instead of taking a simple average, we will take a weighted average. Weighted average, like for example, I want to give high importance to a recent time period. Okay, so I want to give a recent time period is 50% weight plus maybe a 0.3 times of the previous time period plus a 0.2 times of previous to previous time period, for example. So this is the place we call it as a weighted moving average. Again, the question is the weights, how it will be decided, etc. There is no rule around that. We'll discuss about what is that weight will be calculated. So you understand what is weighted moving average and the centered moving average. Centered moving average of 3. So centered moving average means it takes the average of 1 time period here and 1 time period previous, 1 time period past, sorry, future. So this is what we call as a centered moving average. So centered moving average of 3. So centered moving average of 5 means it takes the current period, 2 time periods back, 2 time periods past, future. So that is a centered moving average of 5. So basically, over the time, we are calculating the averages. So that is what we call as a moving average. And of course, if I give, instead of taking a simple average, I'm giving a weights to each, the time period, and that's what we call as a weighted moving average. Centered moving average is nothing but when we are taking the average, we take a future, we take a past, and that will be considered as a centered moving average. So this is how the concept of moving average looks like. But now the question is, how will you decide it? Is the moving average, can be used as a technique. Suppose if I'm taking a moving average as a technique, what is the moving average of technique? So for example, if I'm taking this one, what is the last 4, time periods average? This will be my forecasted value for next quarter. This is my forecasted value for next quarter. Are you able to follow me? What I'm saying? So in this kind of scenario, what I'm trying to say is the moving average is a simple. Once you decided, you want to take a moving average of 3, or moving average of 4, moving average of 5, and you can automatically consider that value as a forecasted value for your future. But the question is how to decide, do we need to take a moving average of 3, or moving average of 4, or moving average of 5 or something. So that's the place, the calculation of that matrix. You guys remember the matrix? You take the, MAP for moving average 3. So in that kind of scenario, what is the error? This is my current, this is my forecast, and to take the, in absolute, and to take the actual percentage. So this is what we call it as and to take the average of this one. And the same thing I can also do for what? Moving average 4 also, the actual sorry, absolutely. So in this case, which one is giving less average, less error? Sorry. Okay, if you take this one, which one is giving less error? Probably this one is giving less error. Probably we will choose moving average of 3 instead of moving average of 4. Right? So, but generally we don't use moving average as a technique to solve the problem. But yes, if the data is very less, so probably you can think about moving average of 3 or moving average of 4. That will give you the little better solution than rather than using a simple average. And even weighted moving averages, how weights will be decided? Which weights are best weights? Whichever gives you minimum error, that will be your best weights. Right? But I told you moving average a lot of times, suppose sometimes this value is missing as a time series. Now what we will do is, instead of taking the some kind of a overall average missing imputation, what we take an average of a 3, lost 3 or 4 or something like that, we will take it. Instead of taking some value, we will take moving average of the previous values and impute that value. And typically, the moving average when we are doing a imputation, etc. This is the process. Not only imputation, as a technique also. A moving average perspective. If the data is quarterly, the moving average of 4 we will take. If the data is monthly, moving average of 3 will be works better. If the data is weekly, the moving average of 12 or moving average of 4 can works. Right? So these are the typical, if the data is in a daily and moving average of 7 or moving average of 30 works better. Right? So this is how you will impute the, taking the moving average of 7 or moving average of 30. Right? So are you clear on this? Am I correct or not? Now you understand what is the concept of moving average. Okay, so what is the advantage with the moving average? For example, if you look at this one, moving average, suppose assuming that these are the things. Now let's see, how the plots looks like. Now if you see that, you see there is a lot of fluctuations in the data, in the original data. But if you see the moving average of 3 or moving average of 4, whatever it is, this has less fluctuations, the data gets smoothed. So this itself is indicating some kind of a trend in the data. When you look at the moving average, can you see that this is more like a trend line rather than fluctuations? So that's how the moving average works as a trend line rather than normal data. So a lot of times to identify trend, Okay, impute missing values, and forecasting, I mean short-term forecasting if you have a less amount of data, and identifying the trend line. And these are the uses which we use moving average. Are you clear now? Any questions on the moving average, weighted moving average, center moving average? Any questions on this?
Chandra,
Yeah.
yeah, can you show one example of the missing value imputation with the help of moving average?
I just showed you, right? So if this is, look at this one, what I'm saying is if this is a missing, what I'm taking is take the average of the previous 3 values or previous 4 values. Suppose if the data is quarterly basis, probably, what you can say is this is, I'm taking a moving average 4 is ideal. If otherwise you can do the backward filling. What is the backward filling? Taking the average of this one and fill this one. If it is an ascending order, the data is in descending order, probably you can take this one. The trend is a negative trend, probably you can take the average of this one and you can fill it the next 4 quarters. Or you can take the average of this one and you can fill it this quarter.
One more average is there, right? Exponential moving average. What is that? The same as weighted moving average?
No, weighted moving average is different, and exponential, of course, exponential average is something similar to weighted moving average only, because at the end of the day, you're taking the weights in a different manner. That is what we call the exponential moving average.
So, Chandra, how do we decide the weights? I mean, is it
Just now I discussed it, right? The weights is whichever weights gives me a minimum error. The minimum error is minimum MAPE. Suppose by taking the weights is this one, you can calculate what? You can calculate the error. Now by changing the weights, okay, instead of taking a 0.5, take 0.6, and this is a 0.2. Sorry, 0.2, and this is a 0.2. So now you might get different values. So you can also calculate the error, and whichever error gives you low, and that weights are better. But then now the question is very iterative process is very difficult because thousands of combinations are possible. That's the place in Excel you can't really do that, but that's the place it requires some kind of optimization. This will be converted into optimization function and do that. So that's the place, the Excel solver. If you know the Excel solver, you may leverage Excel solver, and you can identify the best values for weights. Otherwise, in the Python, etc., you already have the existing functions. Automatically, it will calculate your moving average and it will give you that.
okay? So it's about finding the right weights.
Yes, right weight which gives you minimum error.
Yeah. Okay.
Cool, perfect. So now let's talk about the ETS models. So the ETS models is, for example, the data is something like this. Okay, the ETS models tells me that this also called as a exponential smoothing models, or this is what we call the econometric time series models. This also we called as a smoothing models. This is also called as a hole to winter method, and these are all different names. So what is this means is my YT is a function of my previous value and a previous error value. YT is function of my previous value, my previous error value, something like this. YT equal to alpha times of ET minus 1 plus 1 minus alpha times of YT minus 1. So what is this tells me that my, suppose you forecasted value, for example, this is 300. In the beginning, you have your YT is something, and then your error is basically what? So this is your forecasted value, for example. and your error is in the beginning. What is your error? 0. Then your this value is a function of this 300 and 0. And suppose you forecasted this value is a 270. And what is your error? Minus 70 is the error. And my next value is depending on my previous value, that is a 200, and my error is minus 70. So the next value will be calculated based on this 200 and minus 70. Is that clear? So that's how your the ETS model works. Now the question is, in this case, what is this alpha? Is a weight. Basically you need to identify a right value for alpha. That's nothing but which gives minimum error. So this is what we call it as a single exponential smoothing models. So there is a double exponential smoothing model. Is my yt is a function of yt minus 1 and yt minus 2 and et minus 1 and et minus 2. So that means my current value is a function of previous 2 values and the previous 2 errors. And in this case, you will have a 2 weights. One is alpha, one is a beta. And similarly, triple exponential smoothing. So my yt is function of yt minus 1, yt minus 2, yt minus 3, and et minus 1, et minus 2, and et minus 3. So that means my current value is function of previous 3 values and previous 3 errors. And of course, in this case, alpha, beta, gamma. Okay, so generally, a single exponential model works so this works when is basically if there is no trend and no seasonality in the data. Double exponential works either one of them, either trend or seasonality exists. Triple exponential, both trend and seasonality exists in the data. So that means that the triple exponential gives you better results if the data is having a trend and seasonality. If the one of them trend or seasonality you have it, double exponential might give you a better results. And no single exponential means if the data doesn't have any kind of a trend and seasonality and the series is stationary kind of a thing, and that kind of situation, the single exponential will give you better results.
Chandra, one doubt.
Yeah.
You were just telling about if my beta is there, then either trend or seasonality exists.
Mm-hmm.
I don't know I'm right or wrong, but if beta is exists, then my trend is there. Sorry, seasonality is there, not trend.
So you are saying that so the double exponential works well if the data have a seasonality.
Yes, and triple exponential if data has trend. Well, I don't know, but I'm just clearing. I want to clear my doubt.
This is, I'm sure, this is works if the data have a trend and seasonality, and then it works gives better result, and this is also gives better result. But in this case, again, there is no. These are all our best practices. These are all not fixed rules, right? So my understanding is, this will give you. If the data have a trend or seasonality, one of them. But since you pointed out this one. Probably I will also cross check it once again. But based on my understanding, if the data have either one of them, then it gives you a better result. That's what my understanding. But I need to check it if you have any kind of a clarifications required.
So why I was saying that there's no need for a double exponential or triple exponential if gamma is plays for both trend and seasonality, and alpha is also playing for both either trend or seasonality. So if only one exponential is enough, if such kind of scenario is there.
Probably you might be, your logic is correct, but let me check that.
Okay.
Okay. But yes, these are the typical scenario. You can think about this one. Okay, so this is what the single exponential, double exponential, triple exponential. Now the other one is ARIMA model. So when I say ARIMA model, so basically first I need to explain what is AR model. So what is AR model? AR is nothing but autoregressive. So what is autoregressive model? Autoregressive model is nothing but my current value is a function of my previous values. So I don't know how many previous values. I'm assuming that my current value is function of past p values. So if this is the case, what I'm saying is this is nothing but beta 1 times of yt minus 1 plus beta 2 times of yt minus 2 plus and so on, beta p times of yt minus p plus constant. So this is nothing but what? Yt equal to beta 1 times of lag 1 yt, of course lag 1 I'm talking about, beta 2 times of lag 2 plus beta 3 times of lag 3 and so on, beta p times of lag p plus constant. Correct? So that means that my current value is a function of past n lags or my past p lags. So that is what we call as autoregressive model. If you are able to establish that relationship. So this is simple like a linear regression, right? If you know how many lags you need to take, then you know that it's a simple x, y you have in x1, x2, x3 you have it, and just establish the relationship. Correct or not? In this case, the question is how many lags I need to consider. So that is nothing but we call it as the order of AR is nothing but the P. So basically you need to identify what is the value of P. Right? So this is what we call it as autoregressive model. And there is another, in this case, the moving average model, not that moving average what we discussed in the past. In this case, the moving average model is basically my current value is a function of previous errors, et minus 1, et minus 2, et minus 3, and so on, et minus q. So this is nothing but my yt is a gamma 1 times of et minus 1 plus a gamma 2 times of et minus 2 and so on, a gamma q times of et minus q plus some constant 2. So this is what exactly we call it as a moving average model. It's called moving average. So in this case, what we need to know, how many past errors to be considered as part of the model. That is nothing but order of MA, that is nothing but Q. So basically, when the data have, either it can be a function of past values or it can be a function of past errors. It can be a function of past values or it can be a function of past errors or it can be a function of combination of past errors and past values. So that is the kind of scenario which comes under ARMA model. What is that ARMA model? It's autoregressive moving average model. So what is that? It is nothing but my yt is function of f2 is yt minus 1, yt minus 2, and so on, yt minus p, comma, et minus 1, et minus 2, and so on, et minus q. So this is same as my yt is a function of that is nothing but beta 1 times of yt minus 1 plus beta 2 times of yt minus 2, and so on, beta p times of yt minus p plus gamma 1 times of et minus 1, gamma q times of et minus q plus constant p. So which is nothing but it's a cost n terms, p terms, and cost pq errors we need to find out. So in this case, the order of ARMA model is, you need to know p and q values. Does that make sense? So this is what we call as the autoregressive moving average model. But whenever we are performing the autoregressive or AR or MA or ARMA, the prerequisite is the model should, the data should be stationary. If the series is stationary, you can perform AR model or MA model or ARMA model. But if the data is not stationary, then you will have a model called ARIMA model. What is that? AR and I and MA. So as you know, autoregressive and moving average. So, and the third one is integrated. So autoregressive means cost p terms and the cost q terms, q errors. And this is a number of times to difference the series to convert stationary. So what does that mean? Since your series is yt is not stationary, right? Yt is not stationary. So how many times I need to take a difference? How many times I need to take a difference? And that is what we called as a D. D times you need to take a difference to convert a non-stationary series into stationary series. So in the order is, in this case, is what? D. So that means that P, D, Q. So this is same as a, suppose a series is yt is not following stationary, not stationary, and you converted, for example, d equal to 2, you got it. That is nothing but after 2 times of difference in the series, that is nothing but a diff of 2 yt is stationary. Okay, so diff yt is assuming that zt. Now I can use zt for building a model. That means ARMA model, I can do that. So then what I'm building, when you say ARMA for zt, what is your this one? zt will be, okay, a function of zt minus 1, zt minus 2, and so on, zt minus p, comma, et minus 1 and et minus 2, and so on, et minus q. Because when I'm saying the series is not stationary, you convert it into stationary, then that series you need to use it for building a model. So this is how you will be able to build a model when you are building a ARIMA, right? So ARIMA, when you want to find out the order of ARIMA is nothing but what? P, D, and Q. What is the PDQ? What is the PDQ? The PDQ is nothing but the order of, that is number of past, how many terms you need to consider from the past. D is nothing but number of times you need to difference the series. Q is nothing but number of past errors. So this is what the order of AR and MA and I. So when we are referring to that ARIMA model, there are 3 stages of modeling.
Chandra,
1 second. 3 stages. First is identification stage, and second is estimation stage. The third is forecasting stage. So when you say identification stage, that is nothing but you need to identify values of P comma D comma Q. Okay, assuming that, example, my order is order of P comma D comma Q is, for example, 2 comma 1 comma 1. Okay, 2 comma 1 comma 1. So using this 2 comma 1 comma 1, I will get to know what is my equation will be. Am I correct or not? So that equation, you will try to solve your betas and you will estimate betas and gammas, so that you will get mathematical equation. And the forecasting, using this mathematical equation, you can forecast, because you know YT is a function of my past n terms and past errors. That means my next term will be, I can forecast the values, right? So that is the 3 stages which we can think about. Now, the most important thing is identifying the PDQ values. So this is the place, there are 2 approaches we have it. One approach is using a methodology called Box-Jenkins methodology. And there is another way of doing is, for a different combination of, this is what we call as a grid search. For a different combination of PDQ, build different models, and whichever model gives me a minimum AIC value for a different combinations of PDQ. So that means that P equal to 1, D equal to 1, Q equal to 1, P equal to 2, D equal to 1, Q equal to 1. So like this, change the values of P, change the values of D, change the values of Q, you will get a different models, and whichever model gives me minimum AIC value, that will be considered as a best values of PDQ. So this is the another approach we use that. So once you know this PDQ, then this is just like a regression to estimate the betas in this one. So end of the day, it will use a simple concept like linear regression. And once you know the mathematical equation, then using that mathematical equation, you can forecast and you can calculate the errors. And that will give me how good is your model, right? So this is the typical ARIMA process, how it works. Okay, I think someone asking questions.
Yeah, Chandra, you have just talked about PDQ, which is in the small case, right?
Yes.
Yeah, certain thing is there like the uppercase for PDQ.
We'll discuss about that. Just give me a second.
Okay.
So ARIMA, whenever I'm referring that, this is nothing but a small PDQ. Okay, but in some reasons, the data has seasonality within that. Okay, seasonality or cyclicity or something which you have in the data, then you may not able to use ARIMA, then you need to use seasonal ARIMA. What is seasonal ARIMA means? So in this case, the seasonal ARIMA is nothing but you will aggregate the data. Suppose the data is in a weekly or monthly or something, and you will aggregate the data yearly, and you will also calculate the PDQ values for that series. And then you will also get the order of PDQ, and that order of PDQ we call it as a capital PDQ. So that means the data will aggregate it at every year or whatever the time period you want, you can aggregate that, and whatever the rest of the series you're getting, and that is what exactly we call it as a PDQ. And for that PDQ, we call it as a capital PDQ. Those are seasonal parameters. Those are seasonal series parameters. So that means that if I look at ARIMA, you will have small PDQ as a order. If you talk about SARIMA, small PDQ and capital PDQ. And what level of aggregation you will do that. That is a seasonal parameter. Right? So you understand what is the ARIMA versus what is SARIMA? The ARIMA, if the data is stationary and there is no seasonality, no cyclicality. But if the data have some kind of seasonality and some stationarity, and that kind of situations, you will use seasonal ARIMA. That means the data will be aggregated at yearly wise, and you will calculate the PDQ values for that new series, and that is what we call as a seasonal ARIMA. And I think till now what we discussed is ARIMA, but there is another thing which is called ARIMAX. What is ARIMAX? Suppose you have a series like YT like this. This is YT, assuming that. And you also have some X1, X2, and X3, and X4. Assuming that these are the 4 variables, again, these are also indexed by same time period. So now what I'm saying is my current value is a function of my past value, past errors. That is one kind of a thing you are talking about. But this value is also a function of some other factors which are contributing. Whatever that is contributing. So indirectly what I'm saying is, when I talk about ARIMAX, ARIMAX is basically a function of YT minus 1, YT minus 2, and so on, YT minus P, comma, ET minus 1, ET minus 2, and so on, ET minus Q, comma, X1, comma, X2, comma, X3, comma, X4. Are you able to follow me what I'm saying? So that is what ARIMAX model. ARIMAX is nothing but ARIMA with X variable. ARIMA with X variables. Are you able to follow me or not? So SARIMAX is nothing but SARIMA with X variables. So that means that suppose when you are performing ARIMA, there will be some errors, right, in the ARIMA also. Right? After performing a model, you got some errors. But how will you address that errors? And that errors probably you can address with the help of some X variables. That X variables which we can consider for the as part of the forecasting. So end of the day, in this case, what is your mathematical equation like? My mathematical equation will be beta 1 times of YT minus 1, beta 1 times of YT minus 1 plus beta 2 times of YT minus 2, and so on, beta P times of YT minus P, plus a gamma 1 times of ET minus 1 plus gamma 2 times of ET minus 2 plus, and so on, a gamma Q times of ET minus Q plus some P1 times of X1 plus P2 times of X2 plus P3 times of X3 plus P4 times of X4 plus constant. So this is my ARIMAX formula, guys. Mathematical equation. This is nothing but what? Of course, this is YT. So are you able to follow me? How the equations are different for a different types of models? This is ARIMA family of models. AR model, AMIA model, ARIMA model, ARMA model, GARIMA model, SARIMA model, whatever you are talking about. Correct? Okay, cool. So this is what we call as ARIMA model. Then the other one is regression. I also told you regression. So regression is basically, I was referring that, okay, this is the data, you have it, assuming that like this. Okay, so I mean, assuming that some values are filling. Okay, so assuming that this data I have it, now I want to build the model to forecast for next quarters. I want to get the, I want to find out my 13th quarter, what is this value. So assuming that for my 13th quarter, I also have a values of x1, x2, x3, x4. Then only it will works, right? Even Arimax or Sarimax, whatever, wherever it is, I need to forecast for my YT. But for that, you already assuming that you have the values of the previous values. Okay, now, if in this case, what I want to check is, okay, if this is the data I have it, how to build a regression. So typically, first of all, whatever I'm talking about, my YT is first is function of what? Trends and seasonality and irregular component. The irregular component is something which you can't really estimate, but the trend component and seasonal component you can estimate. How can we use trend component? By using what? By using the moving average, I can find out the trend component. And the seasonal component is, there is a methodology to calculate the seasonal component. We can also calculate the seasonal component. So that means that I can find out my trend component. I mean, that is nothing but TT. And I can also find out CT, ST, and whatever the leftover IT, you are able to express with this help of this one. Are my previous values of YT minus 1. So indirectly I'm saying that, okay, you can take a lag 1, you can take a lag 2, you can take a lag 3, etc. That is also sometimes you can take it. And if the data is a quarterly, you can also look at the seasonal component. If you want to take a seasonal component, you can do that. Otherwise, what you can do is the seasonal component, okay, a dummy for quarter 1, dummy for quarter 2, dummy for quarter 3, dummy for quarter, I'm giving a 1 and the rest all 0. Do you agree with me or not? So like this, I can, if the data is a quarterly, I can do this. But if the data is monthly, what I can do? Month-wise, I can give the seasonal component. So that time, if you have 12 months, probably 11 dummy variables you can create, so that you can think about how the dummy variables works. So that's how you can capture the seasonal component. So if the the quarter 1 is really impacting the sales, and obviously the beta coefficient you will get it for that quarter 1, right? Contribution of quarter 1. So that's how you can capture the trend component, which is a moving average. I mean, a moving average component, MEF3 or MEF4 or something like that. And this one you can capture. Okay, this is the MEF4. Why MEF4? It's a quarterly data. You remember I've given best practices. So the data is quarterly. You could say moving average is 4. And the lag variables, which can help you to consider the previous one. And these variables will be considered for a seasonal component. But if the data is a daily basis, then what is the kind of seasonal components I can include? I can include weekend, weekday. That is a 2 dummy variables for weekend, and 1 is for weekend, 1 is for weekday. And is it a Sunday, Monday, Tuesday? That's also you can do. Either weekend, weekday you can use, or Sunday, Monday, Tuesday. That is also you can do. Or month also you can do. Right? Week also you can do. Week 1, week 2, week 3, week 4. So the dummies you can include, if the data is on a daily basis, you can include all the days. That means 6 dummies you will get it. And the weeks, 4 weeks, you will get the 4 dummies. And months, 12, 11 months you will get it. Like this you can also get different dummies which you can include to capture the seasonal impact of that particular variable. So once you have all these variables, these all are considered what? X variables, and this is my Y variable. And now I can run a simple regression and to estimate my variable. So that means that, in future, what are the things I need to know? Anyway, my lags and seasonal component, all of these things I can capture based on the time period which you are forecasting, and based on the previous lags. That means the corresponding lags you have it. Only thing you should know it, these values, the X values. So assuming that X values is a investment of marketing spend. Okay, you also generally know that in advance what is my budget for next quarter. If you don't have that much, that means that you can do univariate time series analysis for X1 separately, univariate time series for X2, univariate time series for X3, univariate time series for X4, and using that univariate time series, you can forecast for next 3 quarters and next 4 quarters, and then you can also forecast this one. Do you agree with me? How this forecasting problems can also be converted as a regression problem and do the analysis. So this is how we can also use a regression as a technique to solve forecasting problems.
Chandra, I have a question.
Yeah.
So I understand that YT is a function of trend and seasonality and irregularity. So irregularity we can remove right now. Trend we can calculate by using MA. But how are you calculating seasonality? I mean, I did not understand this D_Q1.
See, seasonality I just told in the past also, based on the granularity of data, the seasonality can be different forms.
Right.
The data is in a quarterly, so that means every quarter one, you are seeing that there is a trend. I mean, there is a pattern.
Correct.
So quarter one is high sales, maybe a quarter 3 is a low sales, or quarter 2 is average sales, for example. And how to capture that seasonal component? One is by calculating the seasonal component. There is a methodology which we do that. That is option 1. The option 2 is, if the data is a quarterly, I'm including each quarter. Okay, if it is a data, this is nothing but what? This is assuming that you have the year and this is a quarter. Okay, 2015. And 2015, you have a first 4 quarters. And that is nothing but 2016. And again, you have a 4 quarters, right? And of course, so 2016 and 2017. So like this, you have the data. In that case, if I want to capture the influence of quarter 1, I'm introducing a dummy variable for quarter 1. Wherever quarter 1 is there, I'm telling as a 1.
Okay.
And this is how you can capture the influence of quarter 1. And similarly, I can also introduce the quarter 2, so that's also capture the influence of quarter 2. And like this, of course, if you have a 3 n categories, that means you can include n-1 dummies. So of course, you can include 3 dummies. Of course, I mentioned 4, but I'm saying that you can include 3 dummies. And if you don't have the other dummy, suppose if it is a quarter 4, there's 1 minus of these 3 will be the 4th one. So that's how you can capture the influence of seasonality.
And this can be my variables for regression to predict YT. This is what you're saying.
Yes, exactly.
Okay.
Not only that, even some, for example, some of the seasons, for example, in US, the festivals are almost same standard dates because they're following the calendar. But Indian calendar, especially different regions or religions, they follow different type of calendars. So that kind of Indian festivals never be a same calendar years, right? Same calendar days. Suppose my Diwali last year you got it as a October. This year you got it as a November. In 2016, then for example, I will introduce to Diwali flag. So what is the Diwali flag? Which month? Suppose data is you have a monthly data. In which month 2015 you got the Diwali? In which month 2016 you got the Diwali? So that you can capture the effect of Diwali on the total sales. So not only that, if you are introducing some kind of a promotion, like for example, Great Indian Sale, you are doing that. So that kind of situation, which of the days or which of the months you are doing that promotion, so that capture of that particular promotion, you want to capture as a separate term. So that's the place I will introduce a promotion flag.
But this will be on a quarterly basis, right, Chandra?
No, I'm saying that assuming that the data is you have in the
Quarter.
monthly basis or a weekly basis something, and that kind of situation, that particular month, or that particular week, or that particular quarter, you have the festival or not.
Okay.
Is it clear? So like this, you can capture different events effects on my total data by introducing a different dummy variables, so that you can capture that particular event and what is the influence. Is it clear? I think this is the one of the question very beginning someone asked me. What is the effect of some of the events like this? Good. So once you have that events, and once you have the corresponding variables, and you can just take this as my dependent variable, the rest are the independent variables. So that will give you the mathematical model, and you can use that mathematical model to forecast for future. So that's how you can also use regression as a technique to solve forecasting problems. Right? So I think this is the theory aspect of forecasting, guys. This
Chandra,
is the understanding. Yes.
Yeah, Chandra, you just explained about ARIMA, a small PDQ, but in ARIMA there is a capital PDQ. I think could you explain what are those? I think.
So I explained already that one also. So when I explained the seasonal PDQ, suppose if the data you have a quarterly data, then first you will aggregate the data at yearly, so year 1, year 2, year 3, etc. Then perform, identify PDQ values for that series, that what is aggregated series, and that PDQ we call it as a capital PDQ. So that way you are capturing the trend in the aggregated data.
Actually, the small PDQ, just like you explained, it is like auto regression and lag and error. It's a small PDQ, but capital PDQ you have just told is aggregated. How can I'm not able to understand it?
See, guys, this is what I'm saying, that in this case you have two series. One is a granular series, one is an aggregated series. So you have the data at a quarterly wise. You got the you will identify this series like this. Okay, and once you have aggregated series, like for example, if this is a quarter, 3 quarters, so how many years data you have it? 4 years data. So year and sales. Okay, year 1, year 2, year 3. Suppose in this case 3 years data, for example. And that kind of situation, the PDQ values is basically, you can take the total sum of this 4 and total sum of this 4 and total sum of this 4 like this, and then you will get the, for example, this is you got as a 500, this has got 300, this has got 900, this has got is 200, for example. So you get, this is a series, right? For this series, that means that the y2 is a function of y1. So how many past, my current y4 value is how many times it's relating with my past values. So based on that, the PDQ will works. So end of the day, the aggregated series, that is nothing but the YT will be a sum of the the beta 1 times of the last year value, and the beta 2 times of last year value, and last year error, last year error. That's how you will able to capture. So that means that you will have a two series, one series at a granular series, one series at a the yearly series, you know, if you are considering as the time period is a year. So that's what I said, you know, the aggregation at what level you need to do. So that's what I said. The SC is, if I give 4, in this case, the aggregation will be at 4. If SC equal to 2, the aggregation will be at 2. That means semi-year. Does that make sense?
Yes.
Cool, guys. So in that case, you know, the next important thing is the implementation part. As you know, implementation of the time series in Python, of course, pandas will be helpful for all data indexing, importing data, or converting a normal data into time series data, because end of the day you need to convert every data into time series data, and of course doing plots and understanding the you know different aspects of time series, like averages, etc. These are the few things which we can do with the help of pandas. And of course, there is another package which is called stats models. Under that, there is a module called TSA. TSA is nothing but time series analysis. So using this TSA module, you can perform, I mean, like all these a lead, a lag, or you know, difference, you know, stationarity checks. This is basics of this one, and of course conversion of, you know, I mean, conversion means it is just data manipulation step, but then building ARIMA models and doing a decomposition, all of these things can be done with the help of stats models package, right? So in the next lesson, probably we will take one univariate time series and one multivariate time series example. Time series example, and I will show you how to build the models with the help of these packages. Of course, you know, other packages like supporting packages NumPy and you know Seaborn or Matplotlib, you know, these are all our other supporting packages can be very helpful. So in the next class, what we'll take, we will take one example of univariate, multivariate, and then see that how these can be implemented. Good. Excellent. Any questions? The steps is very simple. You know, of course, first what you need to do is import the data as a time series data, or convert a normal series into time series. This is the first thing. And look at the components of time series. So that means that if the data have a trend, if the data have a stationarity, sorry, is the data have a seasonality, is the data have a, you know, that part, that components, you know, you need to understand. And then is the series is stationary or not? And is the data have univariate or multivariate? And identifying the relationships with YT and you know, the X variables, XT, X1T or XT, if it is a multivariate series. So sometimes in the multivariate scenarios, the X1, you know, I told you, suppose marketing spend, the last month marketing